AP Physics C, Electricity and Magnetism, Magnetic Field and Forces, Problem-Solving Techniques. We will have a brief introduction and then a nice summary of the concepts that you learned, hopefully when you read through the presentation on magnetic field and forces. Then we will work 3 problems in very good detail. Introduction. This won't be a typical unit presentation. There are no formative assessment questions to test your knowledge. However, comprehensive magnetic field and forces problems, and there will be 3 of them, are solved step by step. Before going to the next step in any of the solutions, try to figure out what the step will be and work the problem yourself. There are questions in the presentation which you should also attempt to answer before moving on. You can do this on your own, with a group of students, or led by a teacher. Magnetic field and forces summary. Magnetic field lines. They are defined by convention as leaving the north pole of a magnet, like such, and re-entering at the south pole as shown below. The lines specify the direction that the north pole of another magnet in the field will align with. So if I put another magnet here, what will happen, the north pole will be pointing in the same direction as the field lines from this magnet right here. More lines per unit area represent a stronger field, and all magnetic field lines form complete loops and go right through the magnet, just like this. So we have loops. A north pole is always found with the south pole, right down to the atomic level. There is no such thing, at the moment, no one's found one, a magnetic monopole, a north pole or a south pole all by itself. Like poles repel, so a north and north will repel each other. Unlike poles attract. The symbol for the magnetic field is B. Okay, so this is how you'd write it in vector. The field is a vector and has both magnitude and direction. The unit of B is the Tesla, where 1 Tesla equals 1 Newton per amp meter. Because a Tesla is such a large unit, the Gauss is frequently used, where Gauss is 10 to the minus 4 Tesla. But whenever you're using any equations at all with the magnetic field, you have to use Tesla. That's the standard unit. Electric currents produce a magnetic field that radiates in concentric circles from the wire. And we're showing pictures of it down here. The direction of the field is given by the right-hand grip rule, which is an application of vector calculus so you can see what you're doing. You put your right-hand thumb in the direction of the current, and the magnetic field follows the path followed by your curled fingers. So you can see, hopefully on this picture it's a little easier, make all these concentric circles, and at any point here you find the magnetic field at that point by drawing a tangent to the circle. Once again, to find the magnetic field at any point on the concentric circles, draw a tangent line like that, and like this. Okay. That points in the direction of the magnetic field at that specific point. There's no component of the magnetic field pointing towards or away from the wire. To find the magnetic force on a moving charge, use the equation F is equal to QV cross B. And this tells you that if the charge is not moving, if the velocity is 0, there is no magnetic force on it. We find the directions of the force, velocity, and magnetic field by the vector cross product or by the right-hand rule. Point the 4 fingers of your right hand, and we've got that in bold again, just to make sure you use your right hand, in the direction of the charge's velocity. Don't worry about the sign of the charge yet. Curl your fingers perpendicular to your palm and point them in the direction of the magnetic field. Another way of looking at it is just point your palm in the direction of the magnetic field. Now extend your thumb perpendicular to your fingers. That is now pointing in the direction of the magnetic force on a moving positive charge. Now, what if the charge were negative? Now we worry about it. All you have to do is flip the direction of the force. So if the force on the positive charge is up, the negative charge will be down. In case pictures work better for you than that verbal description on a page before, here's a picture. We started with the hand, with the 4 fingers here, pointing in this direction. They were just extended from your hand. We then curled them, as you can see here, where they're in the same direction as the magnetic field. Also, and let me just erase this, notice that your palm is actually pointing in the direction of the magnetic field also. Then extend the thumb up here, and that tells you the direction of the force. Now that's the force on a positive particle. If this were a negative particle, the force would be down into the desk. If the velocity of the charge is parallel or anti-parallel to the field, right? If the B field is like this, and the charge is moving this way or this way, then there is zero force on the charge. If the charge is not moving, then there's also zero magnetic force on it. The magnetic force will always be perpendicular to the charge's velocity. We've done that before when we studied circular motion and also the planets and the moon moving around the Earth. You have a center-seeking force then, which gives you centripetal motion, so the charge in this case, because now we're dealing with a charge and a magnetic force, will move in a circle. So we've injected an electron here into this field, and it will have a magnetic force directed to the right at all times, no matter where it is in the field. That force is making it move in a circle. Now you might say, wait a minute, why is the force that way? It's an electron. Okay? If it were a proton, what would happen? It would be orbiting in the opposite direction. Since the force is always perpendicular to the charge's velocity, it's also perpendicular to the charge's motion. Thus, since work, what's that equal to? That's equal to force dot displacement. Since the force is always perpendicular to the displacement, the work will be zero. And then by the work energy equation, if I have KE plus work equals KE final, and this should be KE initial, there's no work, the kinetic energy doesn't change, so the speed of the particle stays the same. The magnetic force will not change the speed of the particle. It, of course, will change its velocity, right? Because the velocity includes the direction piece, and you can see how the velocity keeps pointing in different directions, but it maintains the same speed. Let's put a whole bunch of charges in motion and create a current. So there'll be a force on the wire that carries this current, and that's equal to, again, it's a vector, IL cross B, right? Very similar to this one, right? QV cross B. L is in the direction of the conventional current, and that's the length of the wire. I is the current, B is the magnetic field. Again, we use the right-hand rule to find the vector directions. Your four fingers point in the direction of the conventional current, okay, which is the flow of positive charge. The palm faces the direction of the magnetic field, and the thumb indicates the direction of the force on the wire. The magnetic field that surrounds a current-carrying wire is calculated by the Biot-Savart law, and this expression was first discovered experimentally, and then the equation was fit to the data. That's beautiful stuff. Ampere's law, which we'll do in the next unit, calculates it theoretically, and what's nice, of course it matches that. Mu zero is the permeability of free space, and it's just a constant. And what's nice about this one is when you use it in this equation, the pi's cancel out. The magnetic force between two current-carrying wires is this. D is the distance between the wires, and the force that wire 2 exerts on wire 1 is equal in magnitude to the force that wire 1 exerts on wire 2. And they are in equal and opposite directions. That's good old Newton's third law. L is the length of the wires, and it has to be the same. There's only one L here. The currents can be different, and you can still work the equation. Wires with parallel currents in the same direction attract each other, and wires with parallel currents in the opposite directions repel. That's almost counterintuitive. When you did like poles, what happens to them? They repel. So you'd assume that, hey, if the currents are going in the same direction, it repels. But nope, nope, nope. Same direction they attract, opposite they repel. This has tremendous applications in motors and generators. So let's talk about the force and torque on current-carrying loops. We will define A as a vector that is perpendicular to the plane of the loop. So if I have a loop of wire like this, the A vector will be perpendicular. It'll either be like that or it'll be into the page. And from the side, there's A, and this will be my loop of wire. The net torque on a current carrying loop due to an external magnetic field is net torque equals I, A cross B. The torque is a maximum when B is perpendicular to A. Now if it's perpendicular to A, that means the B field is going, here let me erase this because we're going to deal with this guy on the bottom. If the magnetic field is in this direction and the loop is like this, you get a maximum torque. If the magnetic field is like this, parallel to A, but perpendicular to the loop, okay, what do you get there? You get zero. You get no torque at all. We then define the magnetic dipole moment as I times A, which then simplified our torque equation to mu cross B. Magnetic flux is defined as B, the magnitude of the magnetic field, times the area it goes through, times cosine theta, or more elegantly, B dot A. The unit for magnetic flux is the Weber. Gauss's law for magnetic fields shows that magnetic monopoles do not exist. When you have a north pole at any location in space, it is paired with the south pole. When you take a closed surface integral, that's this thing right here, in a magnetic field, the magnetic flux through that surface is zero. And that is Gauss's law for magnetism. Because, let's say you have a magnetic field going like this, you know it's going to curl around at all points. Okay, so if I take a surface, for every magnetic field line that leaves, it comes back in at some other point. So the net flux through any closed surface will be zero. When a magnetic field is applied perpendicular to the direction that a current is flowing in a circuit, a voltage appears perpendicular to both the magnetic field and current directions. This is called the Hall effect. The Hall effect also proves that electrons are the charge carriers in electrical circuits. By measuring the Hall voltage, delta V sub h, we can actually derive the drift velocity of the electrons, where there's your Hall voltage that you measure, here's your applied magnetic field that you measure, and here's the width of the conductor or the probe that is that you find the potential difference across. Y, that's in meters. And that gives you directly the drift velocity of the charge carriers, which in a circuit are electrons.